finished visual physiology and got started on the inner ear physiology. That's the last topic for lecture exam 2. So on the sides is the study guide for lecture exam 3. We will start today. We will have a few lectures on lecture exam 3. You might be wondering why we lecture on lecture exam 3 before lecture exam 2. You will see after spring break, we're trying to design the course so that no lab has to do a lecture exam and a lab quiz at the same day.
Thank
It
you.
just warmed up because the last teacher did shut it down, and it takes forever to shut it down.
Thank you.
And it takes forever to start up.
But anyway, sometimes it's unavoidable, but if I can avoid it, I will avoid it. And in order for us to not have any lab do a lecture exam and a lab quiz on the same day, especially just 10 minutes apart, we have to put off lecture exam 2 for a little bit, okay? So there's a reason for it. But we'll be starting on lecture exam 2 material today. Okay, so if you have your lecture packets, turn it to page 34. It shows you some of the physics of sound waves. And you do need to know a little bit about physics to understand auditory physiology. We have covered the other areas of the inner ear, the semicircular canals and the vestibule, and in those regions they have both stereocilia and one kinocilium. In the cochlea for hearing, there are no kinocilia. There's only stereocilia, and they kind of look like a little teepee. Everybody see that? And again, on page 34 in your lecture package is showing you some of the physics of sound waves. They are basically alternating compressed air and what's called rarefied air. So if you imagine throwing a pebble into a pond and seeing water waves spreading out from where the pebble hit the water, that's very much like what sound waves look like, except it's not in 2 dimensions, it's in 3 dimensions. It is spreading out like a sphere. Everybody got it? And the waves in the water, where it is a crest, would be compressed air. The waves where there's a trough would be rarefied air, but it's radiating out from the pebble. Everybody got it? And it is in 3 dimensions, like a sphere. So if you look at the top on page 34, you can kind of see that, the waves, areas of compressions, areas of rarefaction, but that's on a page. It's got to be drawn in 2 dimensions. In reality, it's a sphere, it's in 3 dimensions. Everybody else, any questions? You have to have a medium to carry sound waves. And it doesn't have to be air. You go swimming, go underneath the water in the swimming pool, you can hear sounds in water. Water's carrying the sound wave, but it changes it, doesn't it?
Yeah.
Not only does it much slower, but also it changes the frequency. You listen to your friend's voice in air and they go underwater, it sounds different because the water changes the frequency. Okay? Which means if you ever see any sci-fi movies and you see a spaceship going by and it actually makes a sound, that's bullshit. You should just say that right there during the movie in the theater. Yeah, that's bullshit. In space there is no medium, there is no sound. Everybody got it? Now this is showing you the same thing what's in your textbook, what's on page 34. Again, waves of compression and rarefaction. Like all waves, you have amplitude and frequency. So let's look at frequency first. This can be viewed in 2 ways. From a stationary point, how many crests are coming at you over seconds? How many crests per second? That's in hertz. Or, are you guys listening to this? Is this helpful at all?
Yeah.
Yes.
You can stand off to the side and you could actually, if you could see the waves of compression there's a distance between them going through air, because the speed of sound is constant through air, like the speed of sound is constant but different through water. But it's going through air, water, and if it's a high frequency, the waves the crests are really close together. If it's low frequency, the crests are spread way out apart. It could either be because of the constant speed of sound, either in frequency per second, or in distance between crests.
Whoa. Okay.
Did you guys ever take any physics classes?
No.
Take any physics in high school?
No.
But when you have kids, do not let them avoid hard classes. Because we have, right now, a tremendous deficit in scientific competency. We have a whole generation of adults that can't tell which way is up as far as science is concerned. And I'm not just focusing on you. Yesterday I was driving on the 101. I saw a dude in his car by himself
Oh no.
with a surgical mask on.
Oh my God. People are idiots.
This COVID-19 is a middle-of-the-road bug. It is not particularly deadly, and for this population in this room, unless some of you've got a respiratory ailment that is quiescent, you are not, if you catch it, you're gonna be annoyed for a couple weeks. Why? Because you're not immune, you have to do what's called a primary immune response. It's gonna take you 2 weeks. It is gonna annoy you AF. It's not gonna kill you.
Yeah.
But there are certain things when the whole planet is filled with people who are not immune. We've just got a few tens of thousands of people on the planet that are immune to COVID-19, which means there are over 6 billion vectors for a middle-of-the-road annoying bug. But people don't even know how to conceptualize this. What it means, people, is that the majority of the responsibility here is on governments. There is very little an individual can do. And emptying shelves of sanitizer and toilet paper is saying to the world, I'm stupid as fuck. Who is at risk? My parents are at risk. Anybody who's immunocompromised, who's taking chemotherapy for cancer, anybody who has any respiratory conditions, even if they're quiescent, even if you're a young, healthy adult, if you have a respiratory condition, this bug can kill you.
Like asthma?
So what we have to do is we have to slow down the spread of this potentially global pandemic. Why is it a potentially global pandemic? Because there are 6 billion potential vectors. We have to slow it down for months. Trump wants there to be a vaccine in August. He does not know how these things are developed, tested, mass-produced, and distributed. At the soonest, it's going to be at the end of the year. At the soonest. What are we supposed to be doing? We can't do anything except if you start getting symptoms like a cold or flu, you need to get tested. Except for one thing, our government fell asleep in it, and we are behind the curve in getting test kits out. Other countries jumped on it. Why? They listened to the scientists. Our federal government mistrusts scientists as a monolithic liberal group contributing to fake news and the deep state. Paranoia. And as a scientist, I know that's bullshit. We represent the whole country from liberal to conservative. Understand that? Well, just because someone is educated doesn't make them liberal. It makes them educated, which means this is the goal. slow down the spread of COVID-19 for months, and then there will be vaccines. And maybe this won't kill my parents. Are you catching what I'm saying?
Absolutely.
Panic, you look like that dude driving by himself with a surgical mask on.
I would have died.
Not understanding epidemiology and public health will paint you out as a cold Darwinist. Let's weed out the weak and sickly and the elderly, because that's what's gonna happen.
Mm.
If you're okay with weeding out the sick and the weakly and the elderly, you've got no effing business going into healthcare. There is nothing like a potential global pandemic on an individual basis that separates those who think and care about others, those who should go into healthcare, and those who will only think about themselves, those emptying the shelves of hand sanitizers and toilet paper.
But still buy samples.
On a governmental level, there's nothing like a potential global pandemic to separate those who are intelligent, and that doesn't mean you know everything. That means you know what you don't know. So you listen to the people who do. And those who are dangerous ignoramuses who already think they know it all. Nothing like a potential global pandemic separates the wheat from the chaff, both on an individual level and a government level. You got people out there that are emptying out store shelves. Let them know that's not going to help anything. The most an individual can do is if you start to show symptoms, get tested, if you can get a test kit. But we are behind. And then self-quarantine until you're well. And then you'll be one of those who are immune to it, because it's just a middle of the road bug. Everybody got it? All right. Yeah, I don't know why I went off on that. I just couldn't believe that. It's on the skyline. Not only that, a regular surgical mask, all right, there are masks that actually can have such a fine filter that viruses can't get through. A standard surgical mask, viruses go right through. Not only that, there's gaps all around it. You have to get one of the really skin-sealed masks that has the fibers that can weed out viruses. They are super expensive. If it's not that, don't bother. Anyway. All right, frequency is about pitch. If it's got a low pitch, it's bass. If it's a high pitch, it's treble. The human hearing range is 20 to 20,000 hertz. Human voices are pretty much in this range. Very few human voices are that low, but you hear some of those baritones, bass singers. They have really low voices. But most are around 1,000, 2,000. By the way, when we did the hearing test last week in lab, we went 500, 100, 500, 1,000, 2,000, right? Then this is why I had you do that, number one, so that you didn't waste time doing the whole spectrum. But if you look at those last two diamonds, this is why I wanted to show you that you probably, if you have normal human hearing, needed more decibels to hear the tone at 500, and you needed less at 2,000, because our hearing, our cochleas are actually designed to be most sensitive at the frequency of most human voices.
Whoa, that's cool.
Is that what you guys found out? And there's pure tones where all the crests match up, and complex tones where they're coming at you at all different times. So there's very different ways. Here's a good thing here on the fourth diamond. Because we have a really low level of scientific competency now, you are getting ripped off left and right, and you don't even know. Because nobody taught you how to tell the difference between fact-check, verifiable, objective data and bullshit to rip you off. You have no way of knowing the difference. If you know this, I will tell you this is the ideal range of normal human hearing, and you would probably have lost it by the time you were in kindergarten. Then throughout grade school, the high to lower ends are shrinking. And most adults can't hear anything below about 26 hertz or anything above around 19.5. Then you go out there and look at audio equipment that audiophiles really like, and they're gonna upsell you on something. Hey man, this thing has got a range from 16 to 24,000 hertz. Much better than this other one. You need to get this one. And if you do, your dog will appreciate it. You're not gonna appreciate it, you can't hear the difference. Because you're already inside 20,000 hertz. Everybody got it? Don't waste the money. Use science to protect your wallet. Okay, amplitude, that's volume. Here, we measure it in a unit called decibels. Decibels is not a straight volume. Hopefully they told you this when you went to go do your hearing tests. Because this is what I told all the first groups for both Monday and Wednesday. Decibels is not a volume. It is a logarithmic ratio based on normal human hearing, which means 0 decibels. If it was a volume, 0 decibels is 0. 0 decibels is actually a tone. Minus 10 decibels is actually a tone. Very few people can hear it. There are people that have above normal human hearing. Okay? But this is why this diamond explains it. It's a logarithmic ratio. Every 10 decibel increase is a 10-fold increase. So if you go up 20 decibels, it's not 20 times higher. It's 10 times 10. It's 100 times higher. Every 10 decibels is 10 times higher. Everybody got it? It's a logarithmic ratio. And at about 140 decibels, the hair cells will not just bend, they will break off. That's why it's sometimes referred to as the acoustic suicide spot. You get volumes in that range, depending on the frequency, that spot on the cochlea, those cilia will break off. And you will forever be deaf for that frequency there. Okay? Any questions? Amplitude and frequency. All right, let's just do a little step-by-step hearing. And what I want to do on the whiteboard is I want to contrast the auditory pathway with the visual pathway. I want to try something different this time. So we have the hair cell instead of the rod and four cone. And it has stereocilia only. So let's first talk about the sound waves going through air in the external ear, through solid in the middle ear, it's going through the auditory ossicles, and then through the liquid in the inner ear, perilymph and endolymph. The conversion is happening in the middle ear where the tympanic membrane is catching sound waves in air, in gas, and converting it to the foot plate of the malleus in solid. And the middle ear is like 2 tin cans and a string. Has anybody done that as a kid? You can have a really long string, 2 tin cans on both ends. You poke a tiny little hole area, you tie a knot on the string so it doesn't pull through. You have to have the string kind of taut, and from 25 plus feet away, you can actually talk and hear the other person as if they're right next to you, because the sound waves are going through solid, through the string. And then from there, the foot plate of the stapes is a perfect fit for the oval window. There it gets converted to sound waves and liquid. First in the perilymph, and the scala vestibuli, does that ring a bell?
Yeah.
And then it goes through the vestibular membrane, because it's so thin, and then it's going through the endolymph of the scala media at the same time. Does this look familiar?
Mm-hmm.
So, sound waves in air and gas, sound waves in solid, sound waves in liquid.
Boom, boom, boom.
This is the reason why we did Ryan's test with the tuning fork. So let's see if you guys heard this from the people that were supposed to teach you about doing the tuning fork test. It is checking this bullet. Ryan's test is checking this bullet. The physics of the auditory ossicles actually amplify sound a little bit by itself, 1.3 times. The real amplification occurs when you catch sound waves in something this big, tympanic membrane, and you put it into something this big, the oval window. That's what really amplifies the sound. You know where we see this in everyday life? The stethoscope. It's using the same thing. It's got that big round diaphragm that's catching the sound waves in this big round area, and it's putting it into two little ear holes. That amplifies the sound. Does this make sense?
Mm-hmm.
Same thing here. And that's the main difference, is the tympanic membrane is 17 times bigger than the oval window. So 1.3 times 17, that's how you get 22 times amplification. Everybody got it?
Mm-hmm.
Well, if you dig the tuning fork and you put it on your mastoid process, the sound waves are not doing this. They're going directly through the trabeculae of the temporal bone to the osseous labyrinth. And boom, the sound waves just get delivered straight into the perilymph and endolymph. And you can hear the tone. But you're not having a 22 times amplification. So when all of a sudden this thing gets weaker and weaker, can't hear it anymore, then you put the tuning fork out here. Now you are getting the 22 times amplification, and now you should hear the tone when it died out on your bone. When you didn't have this. Everybody got that? Is that what you were told?
Mm-hmm.
Okay, that was underwhelming. Apparently you weren't told that. You just said, yeah, you're not gonna hear the tone, and then you're gonna hear the tone, and then you just go, okay, then I'll move on. You weren't told any of this? I told all the first groups this.
Oh, well, the first group may have stepped up.
Telephone, party games. All right.
We told them that? I know, but we didn't tell them the amplification part.
All right, so we have two muscles,
I'll take
both sides on the inner ear. This is when you go to a Smoke and Guns concert. Our next show is going to be Barry's. Both sides, these two muscles are going to be contracted. You come see our show because it's just loud. And it's the same thing as taking the two tin cans in a string and putting your hand on it. You're just going to tighten things up, not let the sound waves go through, or not as strongly anyway, and this protects your ears. The sad part is that it does have to respond as a reflex. Reflexes are not instantaneous, so if it's a real sudden loud volume, they will not have time to respond. I had a ex-military, that as a physiology student, and he's right-handed. So when he did his hearing test, this side was actually just a little bit, he had some hearing loss here. He was way deaf in this ear because there's no way for these muscles to respond in time. Okay, so the sound waves go in perilymph first, scala vestibuli, but because the vestibular membrane is so thin, it goes right through it and goes through the endolymph of the scala media at the same time. Again, it's going through both of these chambers at the same time. Now we gotta talk about the cochlea, which turns around the hub 2.5 times. As it's going toward the apex, all three chambers are getting proportionally smaller. It is the shape and size of the chambers that causes different frequencies to resonate at different points of the 2.5 turns. At the point of resonance, it's violent. So violent that the thick basilar membrane actually gets lifted up. And this is what compresses the cilia up against the tectorial membrane. So the hair cell is sitting on the basilar membrane. But the cilia are embedded in a tectorial membrane, and if the basilar membrane is pushed up, boom, it bends the hairs at that spot. Everybody sees that? Basilar membrane is the foundation of the spiral organ. And you can see the hair cells here. But those cilia are embedded in the tectorial membrane. Again, I drew this on the whiteboard. All three parts of the inner ear cilia are embedded in jelly. This jelly in the cochlea is the tectorial membrane. There's only one row on the inner side, multiple rows on the outer, 2 to 3 depending where you are in the 2.5 turns. Weird thing is, it's that single inner row that is the main input for hearing. Okay. So that's what I. And this is showing you different spots of resonance. Higher frequencies are going to resonate here by the oval window. Lower frequencies are going to resonate near the apex, also referred to as the helicotrema. And you can see at that point the basilar membrane is actually going to move, and the cilia are going to be bent against the tectorial membrane. All right. At the spot of resonance, basilar membrane is deflected upward. This bends the cilia. Hair cells generate a graded potential. And this is when it's going to get different. So I wanted to kind of do it side by side. This is the same thing here. But in retina, the bipolar cell also does graded potential, doesn't it? But its neurotransmitter is excitatory, and if it releases enough excitatory neurotransmitters onto the ganglion cell, this multipolar ganglion cell just has to reach threshold by its axon hillock, and it's going to generate an action potential all the way down cranial nerve 2. Does this look familiar from our essays?
Yes.
Hair cells also do graded potentials, and again, the higher frequencies resonate closer to the oval window, lower frequencies resonate at the apex or helicotrema. Easiest way to remember this is that if you're stopped at an intersection and somebody 6 cars away is blasting hip hop even though all the windows are closed, what is the only thing you hear 6 cars away?
The
Bass. Has to do with, again, with bass, the crests are way far away. I'll explain this later. But that just reminds me, over distance, the thing you'll hear is bass. What resonates, you gotta go distance to resonate the bass, way in the end. Does that help at all?
Mhm.
Just keep it straight. You gotta find a way to remember it, find your own way if you don't like mine. The last chamber on the bottom, the scala tympani, that perilymph is to carry the sound waves out to die out. It hits the round window and it just bulges out into the tympanic cavity and absorbs the sound waves, so it doesn't bounce back to re-resonate. So say for instance you got a middle ear infection and there's a big dried piece of snot right up against the round window and it can't bulge out. That sound wave's gonna bounce off the round window, go in, and in those times, I don't know if you've ever experienced this, but if you have a middle ear infection from a cold, sometimes you actually will hear an echo. Because that sound waves will resonate first, wants to die out but can't because the round window has got a big dry piece of snot up against there. Sound waves comes right back in and re-resonates a second time. You'll hear it? All right. This is where it changes. You will notice there's no green cell in this pathway. Okay. The cell bodies for the bipolar cells in the inner ear are in that spiral ganglion. And since the cochlea does 2.5 turns, this spiral ganglion does 2.5 turns. It's shaped like a spiral. And also, and we're not covering bipolar cell physiology, we're just concentrating on multipolar cell, but in the bipolar cell, the action potential actually gets started here. Goes right through the cell body. This is referred to as the dendrite. So in a bipolar neuron, there's one dendrite and one axon on those two poles. And it's the axon of the bipolar cell is the cochlear branch of cranial nerve 8. It's the axon of the ganglion cell for the retina, that is cranial nerve 2. But there is no ganglion cell here. This is cranial nerve 8, cochlear nerve. Everybody got it?
Mhm.
That's what it's saying on the bottom bullet. When I'm lecturing this, you know what students usually look like in the 15 years I've been teaching this? Like how you look right now. I know this is going past you, so that's why I want to draw it out so you can see the contrast. Do you see the contrast?
Yes.
Do the colors help?
Yes.
Okay. Again, point of resonance.
Is it on the lecture plan too?
All right, so here's the pathway. The cochlear nerve is going to enter the brain at the brain stem. So this here, cochlear nerve, is the axon of the bipolar cell. It's going to go to, it's going to end, cochlear nucleus. Going to go up the sides of the medulla oblongata, what we call olives. And again, it's got to go to the thalamus. Here, nucleus, and it's just go through the lateral sides to the olives. Then it's going to go to the inferior colliculus of the forbra quadrigemina. And notice how this is a fork in a road in vision. In hearing, it's all in the same line. Medial geniculate body, the thalamus. This is where hearing synapses at the thalamus. Then it's gonna go to the auditory cortex. On the temporal lobe. This is occipital lobe. So this is mediate geniculate nucleus of the thalamus, but it's gotta go through the inferior colliculi first. So this is for visual reflexes. It's a little more complicated from here. It's gotta go through all the other cranial nerves. This one is just in line. This was a fork in the road. This is in line.
Like there's nothing that stops it, that just goes boom, boom, boom?
There are things that can stop it, yeah. And if it stops it anywhere in here, it's referred to as sensory neural deafness.
Okay. And is each one of those arrowheads a synapse? Like it's synapsing there and then it's going to the thalamus and synapsing there and then
Yes.
going to the, okay.
Yes. Whereas there's no synapse through these
Mm-hmm.
until you get to here. And then there's synapse in there.
Okay.
Okay? Does this help at all?
Yeah.
All right. Intensity coding, if it's loud, you're just gonna get a higher action potential firing rate. It's really just frequency modulation. This is one of the roles of the reticular activating system. We referred to this when we were covering this integrated systems of the brain, and you only have two, the limbic system and the reticular activating system. Does this ring a bell?
Yeah. 100%.
Okay. If you have a lot of background noise, your reticular activating system can actually weed out background noise from things that might be significant, like your name. And so that's why they refer to this as cocktail party phenomenon. You can have a whole bunch of people talking. If you hear your name, boom, your brain will instantly go to it.
Oh, okay. I was wondering what the cocktail
Okay?
situation was.
When I first moved to Los Angeles to go to UCLA, I lived right off the San Diego freeway. I mean right off of it. And that thing was a dull roar 24/7. You can't have 7 lanes in either direction and not have cars on it 24/7. I slept like a baby. Cause that background noise, I mean, I'm pretty sure the 405, unless it was a really loud truck or a horn, that just the cars just going past, it probably sounds what it sounds like in the womb.
It's a scary ass woman.
And it's loud, I mean, it's just loud. But when my alarm went off, my reticular activating system goes, that's not the freeway. And I wake up. Okay.
Makes sense.
All right, how do you discriminate sounds?
Selective hearing.
In your temporal lobe, there is one neuron for every frequency. You can actually hear and distinguish between very similar tones, but they are different neurons for different frequencies. In the cochlear nucleus, this is where we have lateral inhibition. Taking out adjacent weaker signals so that you get more precise information going to your brain. You guys remember where lateral inhibition happens in the retina?
Sorry. Yeah, right there. Horizontal cells.
Lateral inhibition, again, is a CNS process, and most of it is happening in the brain. For hearing, it's happening here in the brain. This is the freak because it's actually out here, which is why neurologists will consider your retina as being part of the brain, because it's doing a CNS process. Okay? Now on the mission. Sound localization. Go ahead and fill in the blanks. Let me just put this up here. This is actually the real reason why all you hear is bass. When you're 6 cars away from somebody blasting hip hop. Is the sound waves are going to, in air, diminish in amplitude after so many cycles. All right, so let's just arbitrarily, this is not actually true, but let's just say in 4 cycles, it starts to go down. Now, high frequency means not only is more crests per second, they're also closer together. Do you remember me saying that?
Yeah.
So, all right, 4 before they start going down. Well, for high frequency, it's just volume. This is going to be louder. Your brain can tell for high frequency, there's where the sound's coming from. Different intensities. It's louder. Everybody got it? For low frequencies like this. Your head, is no way your head's going to be big enough to have 4 cycles for it to diminish. You can't go by that. Does that make sense? Let's see. Let me move this head. That means in 1 cycle, this ear is hearing the trough, this ear is hitting the crest. It's a different phase of the sound wave. That is phase difference. Sound waves are in the wrong phase from one ear to the other. It's out of phase or phase difference. Your brain can actually tell the difference and can localize low frequency sound as well. Crest and trough are different phases. One ear's hearing one phase, the other one's hearing the other phase. So what does the inferior colliculi do? It turns your head. So if it's a high frequency sound, it'll turn your head until the volumes are equal right and left, and you could see maybe where the sound's coming from. Everybody got it? It'll do the same, even though it's not as consciously obvious to you, it'll do the same for low frequency sounds, where all of a sudden both ears are hearing the same crest or the same trough. It's not out of phase anymore, then you can maybe localize the bass sound. It is a little bit more difficult. People usually have an easier time localizing high frequencies, but you can do low as well, like that. Any questions? Okay, you want to put a note right there. That's it for lecture exam 2. That ends lecture exam 2 material. Everything in after this, including hormonal physiology, is going to be lecture exam 3.
So on a study guide for 2, it has the hormone.
Hey, you want to cross it off
Thank you.
and say that belongs on lecture exam 3.
Okay.
Everybody hear that? There's some semesters, hormonal physiology is in lecture exam 2. For you, it's lecture exam 3. So on your lecture exam 2 study guide at the very end, back page, cross it off and say lecture exam 3.
Thank you.
Then you look at the study guide you just picked up, it's copied and pasted here. Lecture exam 3. So we gotta get through this and maybe get into muscle physiology here. Okay. There's actually a rhyme and reason for the order of this, and I don't understand why the teachers want to change the order around, but we are going right now off of organ systems that send action potentials. You guys realize that? Action potentials. What two types of tissues carry action potentials?
Muscles.
Nervous tissue and muscles, right? Muscle fibers conduct action potentials. That's what we're covering. But also I said the nervous system and the endocrine system is the same system. Do you guys remember that? Various parts of the brains are endocrine glands. That's why we got to cover hormonal physiology first. Then we'll get into muscle physiology. So we're going to do mostly skeletal muscle, we will do smooth muscle, and then we go to cardiac muscle. I'm going over the study guide right now. Cardiac muscle starts on page 4. Well, that's where we have to talk about heart physiology. Well, if we're going to talk about heart physiology, we're going to have to talk about blood vessels. That's on page 5, cardiovascular physiology. If we're going to talk about blood vessels, we may as well talk about what's in the blood vessels. Page 6, we're going to talk about blood. Not only do you have red blood cells, you have white blood cells, and the white blood cells are really important in your body's defenses, and that's where we go off and talk about immunology. This is where some of the stuff we're going to talk about is actually relevant for this coronavirus, COVID-19. Did you know that various aspects of this classification of viruses hasn't been around since the 60s? There's been a whole bunch of coronaviruses. This is just the latest version. But that's why you gotta be smart enough to know what you don't know. And if you don't know it, admit it and listen to people who do, and you can act for the good of the people. All right, a hormone, it's a chemical substance secreted by an endocrine gland. Remember that exocrine secretes into ducts to the body's exterior. Does this ring a bell?
Yes.
Endocrine have no ducts, they secrete directly to capillaries, to the body's interior. That is the main difference between exocrine and endocrine, and I have seen a question on that in the TEAS test.
Huh.
You don't need very much hormone to get a response, but it's usually released in response to specific stimulus. Specific stimulus, small amount, it's going to go to specific target cells. Hormones go from head to toe, whole body, but only affects the cells with a hormone receptor. If a cell does not have a hormone receptor, the hormone goes right by it as if it was never there. This receptor works like the lock and key we talked about with specificity. I think it was like the second slide of the semester. Okay? For hormones that have to bind to a receptor on the cell membrane, oftentimes their action is achieved through cyclic AMP, intracellular messenger. You guys remember it? Cyclic AMP, intracellular messenger. Okay. Again, we're covering this now because the nervous system and the endocrine system is the same system. There is a specialty in medicine referred to as neuroendocrinology because it's the same system. And a good way of conceptualizing it is a spectrum, shaded gray spectrum. On one side, the nervous system side, you've got cells releasing neurotransmitters. neurotransmitters travel really short distance, synaptic cleft, have an immediate response, ion flow. It's either gonna be an IPSP or an EPSP, right? And its action is extremely brief. Why does neurotransmitters' action have to be extremely brief?
So they can like reabsorb what they've released back up, so it doesn't keep. That's all I got.
Has to get out of the synaptic cleft.
Has to get out of synaptic cleft, why? I'm thinking more of a functional reason why. You cannot have frequency modulation unless you have individual spikes. On, off. Neurotransmitter effect, on, off, so that the next neuron, because look at all the neurons we got going here. The next neuron can catch that frequency modulation and send it to the next one, all the way through to the auditory cortex. Each one of those arrows is a new action potential. That neurotransmitter has to go boom, 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 so that the next neuron will go boom, 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 boom. Release neurotransmitters that go boom, 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 so that the next neuron hears boom, 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 boom. If that first neuron is boom, 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 you have no frequency modulation. Everybody got it?
Mm-hmm.
For the rest of the chain, the only way you can communicate frequency modulation down the whole chain is if neurotransmitters start immediately, end immediately, short acting. That's what you got on this side, nervous system. On this side, you got hormones. Goes from head to toe. It takes a while for it to finally have an effect, and the effect lasts long.
Mm.
Short distance, short time of action, long distance, longer time of action, and everything in between. You got prostaglandins in the middle. Go a little bit farther, don't go whole body, but there's a whole range of signaling molecules, and it's a spectrum from nervous system to endocrine system. Everybody got it? Understand what I'm saying?
Yeah.
Again, hormones are the key, hormone receptors are the lock. Only those cells with the receptors will be set in motion. Which, by the way, is what hormone means. It comes from a Greek word, hormon, that means to be set in motion. Hormones set specific cells in motion.
Hmm. I like that.
If it has no receptors, again, the hormone goes right past it like it wasn't there. Chemically, there are 4 major classifications of hormones. There are those that are derived from single amino acids. They're called amine hormones. It could either be a single amino acid, or in the case of thyroxine, you'll notice it takes 2 tyrosines. And that puts 2 tyrosines together, actually the R group. Okay? And when you talk about thyroxine, thyroid hormone, you'll see this term T3, T4. See these, that's for thyroid hormone right here, thyroxine. Now look at this thyroxine here. Everybody see the eyes? That's iodine. Same eyes that's up there. This thyroxine is T4. Anybody here know why?
Want to give us a hint?
Count the green dots.
Oh, there's 4.
4 iodines is T4. T4, I believe, is the transported form in the blood, but it does nothing for the cells that get it. Once it gets into the cells, it knocks off one of the iodines. Now it's T3, and T3 is actually the active form in the cell.
Oh.
T4 is the transported form, T3 is the active form, and you just count the iodines. The 3 on it, T3. Everybody got it?
Mhm.
All right, then you can get shorter chains of amino acids, usually less than 100. We call those peptide hormones. Good example of peptide hormones come out of the posterior pituitary. We actually talked about this with the brain, because it comes out of the brain. These two hormones are actually made in the hypothalamus, part of the brain. It's just released at the posterior pituitary. Does that ring a bell?
Mm-hmm.
Now it's oxytocin and ADH, they only have 9 amino acids, and if you look carefully here with a critical eye, you will see that 7 out of the 9 are identical. Only 2 of the 9 are different, at the 3 position and at the 8 position. Can you see it's in bolded?
Yes.
That's specificity for you. Because one is gonna help you to reabsorb water in case you are dehydrated, and the other one's gonna make you squirt out a baby. And the only difference is 2 amino acids.
Damn.
And then you get the really large protein hormones. Insulin is a good example. It is one of the few examples in our body of a quaternary protein structure. You guys remember that? Because it's 2 different chains coming together. Quaternary protein structure. And last are the steroids. So the first 3 are all have to do with amino acids. Just how many? 1 to 2, amine. You get 6 to 100 peptide, more than 100 protein. Steroid is a fatty acid that has been bent and then cross bonds formed so that it forms a classic 6-6-6-5 ring structure. Does everybody here see the 6-6-6-5 ring structure?
Yeah.
It used to be one long fatty acid, okay? All of our hormones, all of them, start out as cholesterol in various organs in our bodies, change groups, change double bonds, and specifically there's a difference between growing facial hair or growing breasts. All right, let's talk about the release of hormones. Here. A lot of what we've been talking about is on page 36 in your lecture packets. The chemical structures of the 4 different types are on page 37. But here we're talking about the stimuli that causes the release of hormones. That's on page 36 as well, right in the middle of the page. In the case of those 2 that are released at the posterior pituitary, that's just neural input. The supraoptic paraventricular nuclei just increase action potential firing rate, and every action potential releases out some more hormone. It looks, do you guys remember saying this? It looks just like a synapse, but instead of a postsynaptic cell, it's capillaries. I actually said that, and if you don't remember me saying that, it's probably when I said it, you had the same look on your face that you have now. Which is why you're probably not remembering it from this time. Yeah, I'm looking at you. I can see that. Okay, I'm gonna do the rest of the lecture the way you did. Neural input, action potentials. Anterior pituitary. Releasing factors. Portal wave. Both 1 and 2 were covered when we covered the brain. With that, I think I used the same pictures.
You did.
When the anterior pituitary gets the releasing factors,
Oh my God.
it releases its own hormones. This is also covered when we talked about the brain. And that's why in the T-test, you should flip down the pituitary gland as the master endocrine gland, because all these hormones, they're targeting the other endocrine glands. Are you guys interested in how these three work together?
100%.
You said that last time, right, and that it's more of a cycle, not, master,
It's a circle, not linear. T-test still wants you to think of it linear. If there's a question on master endocrine gland, right pituitary. If you have to choose anterior pituitary. Because of this. But they work together in a circle. And here's a circle right here. She's going counterclockwise. If you have too low levels of thyroid gland, hypothalamus is gonna send out this releasing factor, thyroid releasing factor. It's gonna trigger the anterior pituitary to release thyroid stimulating hormone. It's gonna go to the thyroid gland. You're gonna get more T3, T4. T4 is the type that is circulating. T3 is actually active in the cells. And then once it goes up, now the hypothalamus is gonna get it and say, well, I need less of this. So then less of that is going to the portal vein. Anterior pituitary is gonna release less TSH, which is gonna cause the thyroid gland to release less T3, T4. That's gonna go back up here and the hypothalamus says, well, that's too low. So I better increase this. This kicks this into gear to release more of this. This causes this to release more of that. Now it's too high. Hypothalamus gets it and goes, hey, that's too much. You see how it's a circle?
Yeah. I got a question for
There
you.
is no master.
Why
It
is
is a
it,
circle.
why is it releasing T4 and T3? I thought that T4 just gets released and then it
Yeah,
loses it.
but it has to do with the feedback loop. Both of them play in the feedback loop. The T4 is the circulated form.
Okay. But it releases both of them.
And so when the hypothalamus gets too little T3 inside the cells, it's gonna release more of this.
Okay.
Everybody see the circle?
Yeah.
Autonomic neurons can actually release hormones or influence the release of hormones. Autonomic neurons that are influencing, say, a parasympathetic response to eating is going to influence insulin and glucagon. Remember that the various organs of your GI tracts are actually sending out hormones in short loops. We tend to not study it during the endocrine physiology because we tend to concentrate on the hormones that go from head to toe. But the stomach is releasing hormones that are going to the duodenum and the pancreas, right? Duodenum is gonna release hormones. It's gonna go to the jejunum. It's basically getting the next part of the donut hole working. Short loop hormones. You want me to explain this picture?
Yes.
I do the picture of the brain and the spinal cord, biceps brachii and the heart. You guys remember that?
Yeah.
And then I had the circle with the ganglion. So I had the red coming down the CNS. The blue was the pre-ganglionic neuron. Synapses in the ganglia to the green post-ganglionic neuron.
Mm-hmm.
This would be the blue one. For the cells of the adrenal medulla, instead of growing an axon, they just stay in the middle of the adrenal gland, in the deep part of the adrenal gland. That's why it's adrenal medulla. They're actually supposed to be post-ganglionic neurons. But developmentally, they said, no, I'm not gonna grow an axon, so they just stay right there. Do you guys remember for the sympathetic side, what does the green neuron release? norepinephrine, actually some release epinephrine. Everybody got it?
Mhm.
The green neuron, if it's sympathetic, releases norepinephrine and epinephrine.
Mhm.
Now, look at the adrenal medulla. I'm not gonna draw it out on time. This is the blue one. All these circles in the adrenal medulla are the green one, releasing the same chemical, except instead of releasing it at an axon terminal on effector, it releases it to capillaries, like an endocrine gland. This is why the nervous system and the endocrine system are the same system. The adrenal medulla are modified post-ganglionic sympathetic neurons. The green ones.
Yep.
Are sympathetic. Let me say it again. The adrenal medulla are modified post-ganglionic sympathetic neurons. That is part of the endocrine system. Do you see how the nervous system and the endocrine system are the same system?
Mhm.
Modified post-ganglionic sympathetic neurons. And again, there's a bunch of different places autonomic neurons are going to influence the release of hormones. And this is a summary of several of those GI hormones. Short loops, only influencing that immediate area and just the immediate area ahead of the digestive tract. And several hormones are influenced by negative feedback loops of certain chemicals. Like calcium would be calcitonin, parathyroid hormone, blood glucose, insulin, glucagon. Sodium would be aldosterone.
What do you mean by plasma concentrations of specific compounds?
Well, like, for example, with blood glucose, if blood glucose levels drop, it'll influence the alpha cells of your pancreatic islets to release glucagon.
Okay.
If your blood glucose goes up, that'll inhibit alpha cells and stimulate beta cells to release insulin.
Okay.
It's going directly off of plasma concentrations of blood glucose.
Okay.
Okay? And so these pictures are basically blood calcium, calcitonin and parathyroid hormone are taken either deposits or withdrawals in the bone for blood calcium, insulin and glucagon on a negative feedback loop for blood glucose, and then aldosterone is about sodium, a little bit about potassium balance. Also on page 36 is how various different hormones set cells in motion.
Mm.
I'm gonna talk about this in a little more detail here at the end. Steroids, because they start out as fatty acids, they are lipid soluble, they go right through the phospholipid bilayer. They have to bind to a receptor inside the cell. Now, the receptor can either be in the cytoplasm or the nucleoplasm. In this picture, which one is it?
What are the options? Cytoplasm or what?
Nucleoplasm.
Cytoplasm? Oh, nucleoplasm.
Nucleoplasm. It's a brown half ball.
Mm-hmm.
This receptor is from the nucleoplasm in here. Everybody see that? Everybody see that? The steroid actually does nothing by itself. It is the steroid receptor combination that sets the cell in motion. And that's why unless a cell has a receptor, that thing, even if it enters the cell, won't affect it. The steroid by itself does nothing. It's the steroid receptor combination that sets the cell in motion. The same steroid can have multiple receptors in the cell, so the same steroid can have multiple effects on cells.
Depending on what it binds with?
Yes,
Okay,
because the receptor steroid combination will target a specific chromosome.
okay,
It's with specificity.
okay,
Different receptor, it'll target a different chromosome
got it.
and a different gene.
Just like the enzyme thing.
This picture shows you both receptors, in the cytoplasm and in the nucleoplasm. Everybody see how it's both?
Mhm.
But it is the combination that activates a gene on a chromosome. Everybody see that?
Yeah.
Growth hormone accelerates synthesis. If the cell is making more of the 4 biologically important macromolecules, it's gonna grow, and it's gonna wanna divide. You get enough growth hormone, you're gonna get growth. But notice here in this picture, it's actually 2 receptors together will bind to this growth hormone. Growth hormone is a protein hormone. It's too big. It does not enter the cell. It binds to a surface receptor. Does not enter the cell.
This looks familiar.
Next to number 3, write individual lab report 8. How many here think that insulin, the function of insulin is to lower blood glucose? Someone's got really super high blood glucose, you give them insulin and it lowers it. How many people think that that's what it is?
Do we have other options?
Well, it's false.
Okay. That's good.
This is what insulin does. You guys ready? Oh, you guys don't care.
Ready.
Let's fill out blanks, because I don't care either. Okay, this next thing here is on page 38.
Where's that? 6, 7, 30. Okay. Hmm? Oh, yeah, I know that's coming, yeah.
Number 4 is actually described on the top of page 38. Number 5 is described on the bottom of page 38. The numbers here in blue correspond to the numbers on the top of page 38.
Okay.
The numbers here in green correspond to the numbers on the bottom of page 38.
Okay.
Yes?
Could you please talk about insulin?
Okay. Insulin opens up both glucose and amino acid channels on the cell membrane.
Okay.
So, you guys remember the links and chains?
Mm-hmm.
Glucose and amino acids are links, aren't they?
Mm-hmm.
What insulin actually does is it puts more links into the cell because it's opening up these channels. If you put more links into the cell, as long as they got ATP, they're going to make chains. Now, what is that called, going from links to chains? Anabolism. The primary function of insulin is to stimulate metabolic anabolism.
Okay.
Has nothing to do with blood glucose. The primary function of insulin is to stimulate metabolic anabolism by putting more links into cells. Then cells will make chains out of it. Now, if you got trillions of cells doing this, both blood glucose and blood amino acids is gonna drop. Because they're all going into trillions of cells from the blood. The dropping of blood glucose that sometimes you have heard being done for someone who's extremely hyperglycemic, they just give them some insulin, boom, it goes down, is not the primary function of insulin, it's a secondary side effect.
Okay.
The primary function is to stimulate metabolic anabolism. Blood glucose and blood amino acid drops as a secondary side effect. And it's this bullet here that is explaining it. It increases glucose transport into the cells. Also amino acids into the cells. From where? The blood. When trillions of cells are doing it, blood levels of those drop. Does that answer your question?
Thank you.
Just follow this slide, play it. Don't just go off the PowerPoint handout. Open the thing on your computer, run the numbers one at a time, reading page 38. I'm gonna make you guys do some work. I think the thing is I'm doing all the work here, and that's why you guys look like this. I need you guys to do the work, and then maybe your faces won't look that way. So do it on the slide. Any questions? I made it easy for you. Same numbers here, blue numbers top half, green numbers bottom half.
Okay.
Again, cyclic AMP is gonna really skyrocket once. Oh, I'll give you this hint. Number 4, top of page 38 is about the hormones that never get into the cell.
Okay.
That's why you need a second messenger. The hormone is the first messenger. And if you're a steroid, the first messenger just binds to an intracellular receptor and actually directly influences the cell, because it's inside the cell. For large protein hormones, look right here, it never enters the cell. This is the first messenger. Well, how do you get this cell in motion? You need a second messenger, and that's the cyclic AMP. The second messenger. Now figure it out. That should give you enough to figure this out. And the amplification is that it's not 1-to-1 ratio. It's 1 to 10, 10 to 5,000, 5,000 to 2.5 million. That's why it amplifies. It's not a 1-to-1 ratio. Okay? And then we'll get to muscle physiology
Next week.
on Wednesday.